Okay, so bear with me, I'm trying a new recorder today, but hopefully at this point you have already watched the videos that I posted on the particle wave duality and uncertainty and all those wonderful things that you were probably freaking out and saying, oh my goodness, this is just too much. What does this mean? What am I supposed to know about this? And so on. So the goal of this video that I'm posting is to give you kind of a broad overview as to where we're going in this unit, what you in broad strokes need to understand, and trying to kind of tie it back into what you're already comfortable with and what you've seen before in general chemistry, though you may not remember it. Okay, so this is about atomic orbital theory, quantum numbers, and the mapping of electron configurations. Okay, so let's start somewhere where we're all comfortable. Remember Niels Bohr? He was the guy who came up with the idea that I can basically imagine an atom like the solar system, where I have the nucleus in the center, and that's kind of like the sun, and then I have the different electrons orbiting around the nucleus. And remember he said that there are basically these fixed orbitals or circular pathways where the electrons are going to go around, and the lowest one, we'll call it orbital 1. He can fit 2 electrons, and then I have orbital 2, he can fit 8, and 3, he can fit 8, and so on. And the basic understanding, or the basic idea, is that the closer to the nucleus you are, the lower energy you are. So you have to fill the inner orbitals before you can go to the outer orbitals. So here I'm looking at a Bohr model of sodium, and I know that sodium has 11 electrons, and how do I know that? Because on the periodic table, his atomic number is 11. Okay, and in case you forgot, the atomic number, while it does directly tell me the number of protons, because that's what defines an element, remember that protons are positively charged, and that means that if I have 11 protons, and every atom on the periodic table is neutral, I must have an equal number of electrons, which are negative, to cancel out that positive charge. So basically from the atomic number, I can get the number of electrons for any element. Now that's not to say anything about the different ions that are formed from that element, but at least for the actual element itself. So basically if I wanted to make a Bohr model, what I would do is I would look at the total number of electrons, I would look at the number of electrons each orbital can hold, and I would put them in the lowest energy orbitals first. So I would take the first 2 of these 11 electrons and I would put them in the inner orbital because it can only hold 2 electrons, and then the next ones go into the outer orbitals, which each hold 8. So I have 2, I have 8 in the second orbital, which gives me 10, but I need 1 more, and that's going to give me this 1, our valence electron, which, if you remember, this is why sodium is so reactive, right? So if I look at a Lewis diagram of sodium, he has that 1 electron that he's just desperate to give away so that he can reveal his super sexy inner valence shell. Okay, so that's Bohr diagrams. I think we're all pretty comfortable with that. Okay, so what does this have to do with this super complicated electron mapping molecular orbital, or atomic orbitals actually? Well, remember when you did electron configurations, you probably started with a map that looks something like this. So you have these different regions. You have the 1s, or the S block. You have the D block, which you probably didn't talk too much about. You have the P block, and you have the F block, which I'm pretty certain none of us talked about, even in pre-AP chemistry. But basically how you use this is you would get a question on the exam that would say something along the lines of, given this element over here, let's pick this one. Oh, no. Sorry, I'm still getting familiar with this. I want my pen. So given this element right over here, what's his electron configuration? And you would say something like this. Okay, the way I taught it anyways, I told my students to imagine that this is something like a hotel and you're trying to give someone directions to get to your room, which is the one I've circled, but they have to walk past every other room and they can't take the elevator. So you would say something like this. Okay, if you're trying to get to my room, you would have to start on the first floor, and you would go past the first S room. then you would have to go past the second S room. So you would tell them that by writing it like this. It's like you're writing shorthand. 1S2, telling me first floor, the S rooms, you have to go past 2 of them. Then I would say, now you go to the second floor, you have to go past another 2 S rooms. Then you're going to go past on the second floor 6 P rooms. So second floor, it's the P block of rooms, and there's 6 of them. Then you'll get to the third floor. On the third floor, you're also going to have to go past 2 S rooms. And then you'll finally go past 1 P room, and you'll get to mine, the second P room. So this would be something like the address you would give, and this we call electron configuration. Imagine that's an N. So you probably left it here and you didn't talk too much about what this actually means, but in reality, just like you're trying to give someone directions to find your room in a hotel in this example, this is kind of the idea that we have for electron configuration in these atomic orbitals, but instead of giving someone a hotel room, you're actually trying to get them to understand where the electrons are inside an atom. Okay, so then you probably made something that looked like this. So for example, for sodium, sodium is in the third period, he's in the first column, so you have to go 1s2, 2s2, past all the P rooms on the second period, and then once you get to the third period, he's the first S. Okay, if you took it a step further, maybe you talked about what those letters actually mean. So the S, right, the S refers to the shape of the molecular orbital that the first electrons are in. So S are these circle ones. The P are these ones that kind of look like, what's the word, like dumbbells, but they go along the 3 axes, so the XYZ axes. These are going to be your Ds, and these are going to be your Fs, right, based on where on the periodic table those electrons are found. Okay, is this too much? Let's take a step back. So going back to our Bohr model, I think we can all agree that we felt pretty comfortable with the idea that we were able to find the number of electrons from the periodic table. We understand that they go into these different orbitals, that the different orbitals have energies, so let's call it orbital 1, 2, and 3. I think we all feel pretty comfortable with the idea that the lowest energy, right, which I have to fill first, is the first orbital. Then once I've filled that one to capacity, I'm going to move to the second one. And the second is going to have higher energy than the first, but less energy than the third, and so on. There's a problem with this, though. Even though it's pretty easy to understand, the problem is that it's not true. In reality, electrons don't behave like planets. They don't just simply orbit around the nucleus in these nice, easy-to-follow circular paths. To some extent, they behave like they do. So it's a good simplification, especially because it allows us to find the valence electrons pretty easily, which we know determines a lot in terms of the chemical reactivity of an element. But think about it this way, right? Sodium and potassium both have only 1 valence electron. And to a close approximation, they behave similarly, right? They're both kind of silvery metals. They're both pretty reactive in water, oxidize easily, but they don't act exactly the same. So obviously, even though they have the same number of valence electrons, that's not the full story. There has to be something else going on. And the something else that's going on can be explained in terms of these atomic orbitals. Okay, so what are we trying to do anyway? What's the whole point? We're trying to figure out where, or kind of where, an electron is at any point in time. Why? Why do I care about where an electron is? The first and most important reason is that HCC tells you that you have to care. And the second reason is that this explains why all atoms behave the way that they behave. Okay, so in a nutshell, I just said what our goal is. Our goal is to figure out where the electrons are, but we have a problem, and that problem is that we don't have a way to know that. There's literally no way to find the detailed pathway of an electron. If you've already watched the videos that, just ignore that, the previous videos that I talked about, you've probably heard about the Heisenberg uncertainty principle, which states that there's a fundamental limitation to how precisely we can know both the position and the momentum of the particle at any given time. So if we know where it is, we don't know, so we know where it is, we don't know how fast it's going. If we know how fast it's going, we don't know where it is. And the way I remember this is through a joke. as I remember most things through jokes. So the joke goes something like this. Heisenberg is driving on a highway. He looks up in his rearview mirror. He sees the flashing lights of a cop car. The cop pulls him over and he says, "Do you have any idea how fast you were going?" And Heisenberg looks at the cop and he says, "No, but I know where I am." And the cop says, "You were going 97 miles per hour." And he says, "Great, now I'm lost." Right, so the idea again being that you can know either where you are or how fast you're going, but you can't know both at the same time. Okay, so what can we do? What we can do is draw a map of where the electron is most likely to be within 90% confidence most of the time. And this is literally what the molecular orbitals are. They're these frequency distributions of where the electrons are. And if that sounds too complicated, let's go back to when we talked about water. So remember how when we talked about what makes water a polar molecule, I said that in theory, for these covalent bonds between hydrogen and oxygen, in theory they're sharing the electrons, but it's kind of like a divorced family. And I said how in theory, again, when you're divorced, you're supposed to share custody of your children, but the reality is that they spend 99.9% of the time with their mom, and occasionally, like every other Wednesday or like Christmas every 7 years, they'll get to go over and see their dad. So I drew kind of like this bulge, and I said that meant that the electrons were mostly around oxygen, but sometimes they went and visited hydrogen. Well, it's the same thing within a single atom, right? So there's these distributions, which is what these molecular orbitals are, that tell us 90% of the time this is where the electrons are most likely to be. Okay, so how do I actually give you the address of an electron? Well, it's not as simple as saying, 7555 Hal Sugarland Road, room 2364. But as with any address, I'm going to have increasing levels of specificity, so I could tell you different things. For example, I could tell you, if you say, "Where am I?" I could tell you I'm on Earth, and that wouldn't be wrong, but it wouldn't necessarily be very helpful. I could get a little bit more specific and tell you the state I'm in, and I could tell you I'm in Texas. Or I could get even more specific and tell you what my house number is. So I could actually give you the house number and the street number and so on. And if I wanted to get even creepy specific, I could tell you what room I'm in, right? I could tell you I'm in my kitchen right now, and my husband is in the room next to me watching football and using my computer and mad that I'm using his. Same thing regularly. Grading. The same thing is true with an electron. However, his address is a little bit more complicated because you're probably not used to asking an electron for his address. So with an electron, we start with what's called the principal quantum number. And this is the one that you already know about this, because if we go to our Bohr diagram, like sodium, right, and we had those nice, pretty little orbitals around him. And I said that you could label them from lowest energy to greatest energy, 1, 2, and 3. These 1, 2, and 3 numbers, that's n. So n is the size and energy of the orbital. So the first one is 1, the second one is 2, and so on. So for sodium, his quantum number would be n equals 3, right? And these also happen to correspond to the periods on the periodic table, right? So sodium is on the third period, and his electrons are going to go up to the third quantum number, the third principal quantum number. After the principal quantum number, like I said, this is only part of the story. That's not really true. They don't stay in these nice, pretty orbitals. We have these angular momentum quantum numbers, which are usually abbreviated lowercase l, which doesn't translate well into text. And this lowercase l tells me about the shape of the atomic orbital. So remember, I had those s orbitals that look like a circle. I had the p orbitals that look like this on my x, y, and z planes. And then D and F, I'm not even going to try to draw. But anyway, these are sometimes called the subshell. And for a given number of n, I can actually calculate what shapes my orbitals can be. And the way I do this is that for any n, the angular quantum moment number L can be the following. So for any n, so for example, if n equals, let's start with something basic. If n equals 1, then the angular quantum number L can equal anything from 0 up to n minus 1. So if n is 1, n minus 1 is 0, so for n equals 1, the only options are 0. But if I look at sodium, where n equals 3,